Hello and welcome to our second undergraduate colloquium of the year. Today we're going to have a presentation from Daniel Hagyard on cosmology, and I hope you enjoy. Please give a round of applause. Well, thanks for attending. It's my pleasure to host our second colloquium of the year. And today I will be presenting my work that I did over the summer on exploring cosmological model beyond Lambda CDM, which is essentially the standard established cosmological model, particularly exploring Axion cosmology, which is a candidate for dark matter, with a phenomenon that's known as the kinetic Sunyaev-Zelevich effect, which I'll get into in a moment. I was lucky enough to pursue this research under the mentorship of Renee Volocek. So she's a professor at the Ultralight Institute for Astronomy and Astrophysics, just next door. And this is research conducted as part of the Physics 378 course. So essentially, the bulk of my research, and well, first of all, the structure of this presentation will be essentially three-part. I will start by motivating the theory behind my research, because I'm assuming that you all probably have around maybe a first-year background in physics, if that sounds right. So I will try to motivate this from as basic fundamental principles as possible. And then I will discuss, once I've done that, I will discuss the theory behind this research in a little bit more detail once I've motivated it. And once that foundation is laid, I will discuss the results. But as I was saying, the foundation of my research is that the model that we use to describe the universe at the largest scales is what's known as Lambda CDM, which stands for Lambda cold dark matter. So this model essentially describes the universe using 6 parameters, which essentially mostly relates to the concentration of various types of matter and energy in our universe. And I'm sure you're all familiar with Einstein's energy mass equivalence, essentially that Lambda CDM describes the universe as having a matter-energy content, and we believe the latest model suggests that 95% of the universe is invisible to observation or interaction with light, and that's what's called dark matter or dark energy. So while Lambda CDM proposes this cosmic energy content that seems to have a majority of invisible matter, it doesn't really describe it in a way that is physically as appreciable as visible matter, which is called baryonic matter. So there's a bit of a problem, because while we know that there must be the majority of the universe is made up of this type of matter and energy that we can't see, we can't, we have significant trouble describing that, what that is. Qualitatively, dark matter and dark energy are believed to drive what's known as cosmic inflation, which is the expansion of the universe. And unfortunately, it's the standard model of particle physics. It does not suggest any promising candidates for dark matter and dark energy. So there's a bit of an inconsistency between how the particle physics model describes the universe and how Lambda CDM does. So, for all the successes that we've had with describing the universe with Lambda CDM, there are some, it's incomplete, and so is the standard model. And my research essentially focuses on particular type of dark matter candidate that comes from string theory called ultralight axions, so ULAs. I'm going to abbreviate it as ULAs from now on. It's a bit of a sort of a tongue twister, but essentially these axioms, as they're called, they come from string theory, and essentially they are a possible candidate for both dark matter and dark energy. So, as you can see in this graph, there's not really a particular mass that ultralight axions have that they occupy. It's possible that there exists many decades of axion masses in what's called the axiverse. So in other words, it's possible for axions to exist with varying masses over the scale on what's called the fuzzy dark matter window, the FDM window. And this window approximately is between 10 to the negative 27 to 10 to the negative 23 electron volts. So while based on string theory, axions can exist anywhere between 10 to the negative 33 to 10 to the negative 10, so beyond this window. This is really just a subset of the window in which axions can exist. Our focus is on this sort of well here, this region called the constrained region, in which researchers are able to constrain the abundance of axion relative to dark matter to below about 1 to 5%. The reason why we're interested in this region as opposed to these regions in which axions can exist with a minimum axion abundance of 0.6 is because, you know, as good as theory is, I mean, we want to detect these axions with galaxy surveys, and essentially this data suggests that overwhelmingly that axions are most stable in this constrained region. So yeah, so ultralight axions are a possible candidate for dark matter, dark energy. And whether or not they manifest as dark energy or dark matter actually depends on the mass that they have. So it's very important to study the mass of axions in this window. But so essentially, some studies, and it's not very clear that you know, the window in which axions can exist. You know, that's a huge. I'm sure you can understand. That's a huge range. You could say that this particle can exist between 10 to the negative 33 electron volts to 10 to the negative 10 electron volts. That doesn't really narrow anything down. But recently, and this study is directly inspired by these findings. Recently, it has been shown by researchers here at UFT in collaboration with researchers at Cambridge and around the world. It has been found that ultralight axions are actually detectable in a much smaller, much more constrained window. So, you know, from 10 to the negative 27 down to 10 to the negative 24, that's a huge constraint from 10 to the negative 33 to 10 to the negative 10 electron volts. And it turns out that we can use what's called, as I mentioned, the kinetic Sunyaev-Zeldovich effect to probe structure growth as a way to measure how implementing theoretically an Axion cosmology can affect structure growth relative to cosmology without axions, sort of a control cosmology, if you will. So I don't expect any of you know what the KSV effect is, but I'll, for those of you who went to Professor Braverman's talk last week, it's actually quite similar to the quantum optical scatter that he discussed. Essentially, when you have photons of light that are, if you can imagine photons of light that are traveling through the interstellar medium, which is called the cosmic microwave background in the context of the study. When these photons collide with massive galactic clusters, you can detect a bit of anisotropy in the temperature of photons based on the Doppler shifting of the frequency of the photon. And since the photons, or the cosmic microwave background, is essentially an ideal black body, the loss in wavelength translates directly to a temperature change. And I'll be a little bit more specific. Essentially, if you interpret the cosmic microwave background, which, for those of you who are not too familiar, is essentially the photons that were released when the universe was first able to create baryon-like matter. Before it was called the recombination epoch, photons were confined to constant scattering with the free protons and electrons in the interstellar medium. And at this point, protons and electrons were able to combine, and photons for the first time gained significant amount of freedom, degrees of freedom to move. So this is what's known as cosmic microwave background, just to get everyone on the same page. As I said, it can be interpreted as a black body. If you can imagine that once these CMB photons were released from constant scattering, they collide with regions of varying matter densities. That will directly influence the temperature gradients of the CMB. So you may have seen these maps before that measure the cosmic microwave background temperature. Well, if you look at these maps relative to matter density maps, and when I say matter density, I mean, as I discussed before, Lambda CDM describes concentrations of matter in the universe, and locally in the universe, we know that density is not distributed equally around the universe. There is galaxy clusters that house billions of galaxies, and then there will be massive amounts of space in between them. Well, that cosmologists believe arises from the temperature variation in the cosmic microwave background. So here there's a figure of, you can see how the black body behavior of the CMB directly influences the density patterns of the universe. So in regions where we have, so the blue represents cooler regions and the red and yellow represents warmer regions. So essentially there's an inverse correlation between the CMB temperature and matter density in the universe. So the reason essentially why the higher amounts of matter density correlates to regions that are cooler is because if there's a higher density of matter in a certain region, the gravitational field will be stronger. So it'll take more energy, photonic energy, for the photon to escape from that region. And this will elongate the wavelength, which corresponds to a lower temperature. So essentially, if you have a region that's warmer, then you'll have smaller density. So this density, this relationship between temperature and density gradient is very important because it gives way to what we call baryon acoustic oscillations. So the reason that we see these matter density perturbations, and the reason why essentially the universe is not sort of an equilibrium of density all over, essentially, is because we know that the photons that consist of the CMB have this quantum pressure that resists gravitational compression of baryon and other dark matter into over dense regions. So essentially, in what's called the primordial sort of photon baryon fluid of the universe, of the early universe, you have this counterbalance between quantum pressure from the photons and the inward gravitational compression of baryons, and this gives way to sound waves, which propagate from these regions of high density. And as I mentioned, they're called baryon-acoustic oscillations. In fact, if you go back a slide, you can see that you can see roughly these DAO shells. It's a little bit more visible in the next figure that I have. So essentially, if you look at the, it's almost like a pattern of temperature variations in the cosmic microwave background, and then if you sort of superimpose later images of density variation in our in modern day universe, you can see these characteristic shells, and that tells you that there is indeed a direct relationship between temperature variation in the CMB, which in turn tells you about density variation in the early universe, and how it relates to density variation at later times. So that's a little bit, I'm sure that's it's a lot of information. If you guys have any questions at this point, that'd be good. Yeah, please.
How do you hear those sound waves?
Sorry, repeat the question?
You talked about how sound waves are generated by what was it?
Yeah, so essentially, when I say sound waves, I really just mean, well, we don't hear them in the sense that, they're still propagating around in the universe or wherever you can detect them. It's more so that, well, if you write out what's called the Boltzmann equations, you get a, I'll get to that in a minute, but essentially you could write out a term that expresses the counterbalance between the quantum pressure term of the photons and the inward gravitational compression of the baryons. And you'll get an ODE that can express the wave-like nature, the cycle oscillations of density variations. So, sound waves, we don't literally detect sound waves in the interstellar medium. It's just that we, if you work out, as I mentioned, the Boltzmann equations, which I will get into in a minute, you see that there is this sort of acoustic oscillatory behavior as a result of the resistance within the photon baryon fluid. So that's a good segue into the sort of, the next part of my presentation, which is sort of answering this question, is that, where do we know that these fluctuations come from? These fluctuations in matter density, essentially, the derivation of this is a little bit too much to fit in one slide, but essentially, if you take what's known as the Friedmann, Lamach, Roberts, and Walker equations from general relativity, and you take the Einstein equations and the Poisson equations and the fluid equations, as I mentioned, because you're approximating the photon baryon sort of primordial soup as a fluid, then you can derive what I was mentioning earlier, the Boltzmann equation. So this second-order ordinary differential equation that describes the matter density perturbations with a little bit more mathematical rigor. So in this term, we have so delta represents the background energy density. Perturbations. So writing this down a little bit more explicitly. If you have these background energy density perturbations, so delta, you can write these out as essentially it's the deviation from the local average density. So rho here represents the background energy, or the energy density at that point in space. And this is just the average. So essentially delta is a measure of how your background energy is like how much it deviates from the average. So with respect to the Lambda CDM, which assumes that the universe is at large scales isotropic, which means it's invariant in density. Essentially, and also it's expanding. It's spatially flat. You can solve this ODE pretty simply, and you get this solution here, which is equation 2. And it has two linearly independent sort of solutions, which can be expressed in terms of a growing Fourier mode and a decaying Fourier mode. And what that means essentially is you have two ways of expressing the perturbations in the background density. One that sort of explains how densities grow, and the other one's how they decay or decrease. And so we have these two linearly independent terms that express your background energy density. You can take a Fourier. I want to make this out of the way. Yeah, so you could take these Fourier modes and you can express the background energy density with more generality as a distribution of these modes. So essentially, the most convenient way of doing that is by taking the Fourier transform and expressing it in Fourier space. And this gives you what's called a power spectrum, which is sort of the most convenient way of expressing intensity of these matter density perturbations in Fourier space. So, this term is the power spectrum in Fourier space, or K space. This is the Dirac delta function, which I'm not sure if any of you guys have seen that. Are you guys familiar with that? Well, anyway, essentially, it's a convenient way of expressing distributions that are Gaussian in nature. And a Gaussian distribution, I'm sure you guys have heard of the bell curve. It's a way of expressing the intensity of these matter density perturbations. So I hear a lot of buzzwords there, like Gaussian distribution, but really the point is that these intensities in the early universe can be expressed pretty simply, at least in Lambda CDM and its inherent assumptions, given the overall complexity of the problem. It can be expressed pretty analytically, surprisingly enough, with this linear perturbation theory. So let's go have a look. Yes, a good example. I decided to put an example of the power spectrum here for various cosmologies, and I'll use this graph as a bit of an aid as I go on to exemplify how applying different cosmologies changes the power spectrum, which is an observable. And that's essentially the crux of this project, is trying to see how applying different cosmologies affects the shape of the power spectrum and what that physically means. But for now, this is an example of a matter power spectrum for various cosmologies. You can see CDM, which means cold dark matter, HDM is hot dark matter. The difference is that hot dark matter in particular is dark matter that essentially is small enough that it can move at relativistic speeds, and this leads to a phenomenon called free streaming, which dampens early matter perturbations. So physically, you can sort of see that hot dark matter moves at relativistic speeds. It causes a phenomenon called free streaming, which dampens matter density perturbations. So in the high Fourier scale, which corresponds to a small real scale, you can see that cold dark matter has perturbations that survive at greater intensity than hot dark matter, which, as I mentioned, at small scales, due to quantum effects, which we'll describe later in the presentation, they suffer from these dissipation at large K scales, which, again, you should interpret large K scales in Fourier space as small distances in real space. So that's pretty much so that's essentially the foundation of this project. So another important term that we can get from the power spectrum, or more generally from linear perturbation theory, is the two-point correlation function, which is essentially just the Fourier inverse of the power spectrum. Essentially, it's a little bit more easy to interrogate the correlation function physically because it represents the probability of finding two objects at distance r from each other relative to a Gaussian distribution. And it's very useful in cosmology, as you can see here, because as an example, it allows us to visualize, to actually see what I was mentioning earlier, the baryon acoustic oscillations. This is a simulation that scales the correlation function by r squared, but you can see these massive peaks in the correlation function plot around the order of in the tens, around the order of 10 to the 1 to 10 to 2. And essentially, what this plot suggests, pretty important, is that relative to a random distribution, you're more likely to find two, in this case, galaxy clusters. You're more likely to find them at this distance, at this co-moving separation r, than relative to a random distribution. And so this is essentially, as I mentioned, it's a feature of the baryon acoustic oscillations. And essentially, this is a pretty good model of how linear perturbation theory gives us this information about how matter clusters at small scales. So, any questions so far? Yeah, please.
So I guess can you explain the difference between the two functions and especially the peak feature?
I honestly, this is an image I sort of pulled off the internet. So it's not related to my project, it's just an example. But I'm pretty sure the difference is how they're calculated, because there's various ways of calculating this. It's not part of my project, but
I guess
the main
physically, is there any reason that
there's a peak
clustering at 100?
It could have something to do with how the correlation function is scaled, because if you were not to scale it by r squared, you would see different shape for the function. Essentially, you would not see this term that's rising here. It would start off from the maximum and then just decrease. I'm not sure if it has something to do with the data that's being in, but what I wanted to focus on was the small scale, right? Because the large scale is not really the focus of my project. The large scale is useful when you're looking at massive scales in cosmology, but since my project, you'll come to see, is more so focused on galaxy clustering, we're more interested in the small scale. The behavior of the small scale is most important. But yeah, I think that it's not really related to my project, this graph. I just pulled it off the internet. But I think the most important thing is that the two plots do share the behavior of peaking here at this small scale. So I just wanted to point out that consistency. So you might be wondering, how is, okay, sure, you can have the power spectrum and you can have the correlation function, but how does that help us understand the relationship between matter density fluctuations in the early universe and how the matter density fluctuates now? Like, how does that tell us about the evolution of matter density fluctuations in the universe? And well, linear perturbation theory in and of itself is sort of constrained to when matter density perturbations in the universe were small, and essentially that was when the universe was sort of young, and at large scales it's really more so applicable. But the power spectrum is useful because early on, as I mentioned, it describes the Gaussian quantum fluctuations that gave way to these energy fluctuations that I'm describing. What's more is that, as we saw in a previous block, I'll go back to illustrate this, the power spectrum is highly adaptable to different cosmologies if you implement what's known as a transfer function. So, for example, and to illustrate this, let's say you have, as I mentioned, a hot dark matter power spectrum that you want to model based off of a cold dark matter spectrum. Well, physically, as I mentioned, when you have hot dark matter, which moves at relativistic speeds, hot dark matter tends to dissipate matter density fluctuations on the small scale, primarily because of their light mass. Because if they're moving relativistic speeds, they will have more mass. It's really naive correlation, but for our purposes, it works. And due to the increased de Broglie wavelength of these very light dark matter particles, it will suppress small-scale structure. So you would expect in the high K limit, which, as I mentioned, corresponds in real space to the low radius, like very small real space limit, you would expect that the modification of a hot dark matter cosmology would be that as you approach this small scale, it would go to zero. And I think that graphically, that's what we see here. You have this cold dark matter power spectrum, and as K approaches 1, you have these dissipations, which can be described by a transfer function that has that behavior. Yeah, please.
Yes, I have a question regarding on the blue graph. Why are the constants not different? 0.7 and 0.3.
It's because, so in this case, if you take, I guess what this means is that if you take, essentially this green graph describes that all of the matter of the universe is cold dark matter. 1, right? So this blue graph happens to suggest that if you take a cosmology that suggests 70%, 0.7 of all matter in the universe is cold dark matter, it gives you a graph that's identical to a graph that suggests that 30% of all the matter in the universe is hot dark matter. So in this case, they just happen to have overlapping behaviors. And this red graph is the most extreme limit, in which case all of the matter in the universe is hot dark matter. So you see that it's dissipated, it has the greatest degree of dissipation, right? So that's essentially the function of a transfer function, is to modify the behavior of a sort of a control power spectrum with your desired traits of, in this case, hot dark matter, or as we'll see later on, ultralight axions. What's more is, as I mentioned, the power spectrum is physically meaningful through its Fourier inverse, which is the correlation function. And as I showed, you can extract roughly the radius of these baryon acoustic oscillation shells through the correlation function, as we saw here. So, yeah, the power spectrum is useful, but the most significant part is not really the destination, or it's more so about the journey than the destination. What's more so important is not the power spectrum itself, but how you derive it. To that end, it's important that we not get too fixated on the observable, but how we got to that observable. So, linear perturbation theory, which until now I've described as the source of our power spectra observable, is only valid at early times of the universe and at large scales when the perturbations were small. So, and this corresponds to a delta of much less than 1. But it breaks down and it becomes insufficient to describe matter density perturbations in the universe as you approach larger density fluctuations in what's known as the quasi-linear regime. So although density perturbations might still be small, the Fourier modes that describe them are changing drastically. So that translates to a non-Gaussian matter distribution. And when you go with even greater density perturbations, you have a significant interference of Fourier modes that describe the density perturbations. And these, this interference of Fourier modes in the nonlinear regime describes what we see as galaxy and galaxy cluster formation. So, in other words, the physical significance of all of this is that while linear perturbation theory is sufficient to describe matter density perturbations in the early universe, it becomes insufficient and it becomes significantly inaccurate when you talk about later stages of the universe. A good remedy for that is something called the halo model in cosmology. So, in order to rectify this nonlinear behavior of, or rather, in order to rectify the breakdown of linear perturbation theory in this nonlinear regime of when you have galaxy cluster formation, you can try to split the power spectrum into two terms, so linearize it, and those two terms are what's known as the one halo term and the two halo term. So I'll step back for a minute, but essentially the halo model, the primary assumption is that all matter in the universe collapses into these spherically symmetric regions that are highly dense called halos. You can use terms that express the relative density in those halos relative to the interstellar medium called halo biases. I won't go into that too much though, because I think it's more important that we sort of understand essentially that the halo model is just, without getting too much into the detail, it's a way of expressing density perturbations at later times without the need to analytically solve Boltzmann equations, which, as I mentioned, is impossible when you reach nonlinear density perturbations. So I think the best way of showing the halo model to people is just showing the schematic, which shows you have this region of galaxy clusters, which, as the paper describes, is a region in an n-body simulation, which is a more computationally expensive way of simulating nonlinear density perturbations. Essentially, if you apply what's known as a halo bias, that I mentioned, the halo bias is a way of mathematically expressing the relationship between matter relative to the underlying density field. So, in most cases, you'll see a linear halo bias. And in this central figure, they've applied, it's pretty hard to see, but they've applied this halo bias, replacing them with these idealized spherical halos, placing all the matter into those halos. And they've isolated those halos in this image to make it easier to see. So I think that the most important takeaway you get from the halo model is that it's the most convenient and it's a computationally inexpensive way of expressing nonlinear density perturbations. Since, as we saw, the linear perturbation theory is insufficient to describe the density perturbations in a nonlinear regime. So if there's any questions before I move on to the next topic, because I've done a lot of explaining theory that's behind my project, but I do want to move on to the results that we actually got from the project. So essentially, my project was using a halo model solver called Axion HM code. That's very new. The most recent edition is the one we use. It was released this year. Is that it uses this halo model to essentially estimate galaxy clustering in nonlinear scales. Now, the reason it's important is that nonlinear scales corresponds to smaller scales with greater matter density perturbations, which is more accurate in reflecting post-recombination cosmology. In other words, cosmology at later times of the universe. And specifically, we applied it to axions, as I started the presentation, I'll describe it, ultralight axions. And what we did was we took the halo model and we forecasted galaxy clustering over the mass window, so between 10 to the negative 27 to 10 to the negative 23 electron volts in terms of mass. Because we wanted to use the halo model to interrogate, can we use this model to model galaxy clustering in this region? And can it impose any more significant constraints on the abundance of axions in that region? So the main goal of this project was to modify the existing halo model code to calculate KSV observables. And so, and as I mentioned, to use statistical methods to constrain the abundances of ULAs in that window, in that constrained window, to see if future galaxy surveys, what axion abundances they may be able to probe with the KSV effect. So, I'll just jump right to the results because I think we're running out of time. We use the code to, first of all, it's important to understand, that we wanted to calculate what's called the mean pairwise velocity spectra. This is our KSV observable that I was mentioning, and essentially it describes the pairwise velocities of galaxy clusters as a result of the KSV effect. So what this tells us is, if you look at, just generally speaking, regardless of the mass window and the abundances, you can see that the most significant result is that there's huge clustering with small scale structure across, it's a little bit harder to see here, but the fractional difference between the velocities of a ULA model to a Lambda CDM model without any axions. There's small scale structure dissipations, or I should say that there's small scale suppression of structure, which, as we described, is expected for axions because of their high de Broglie wavelength. More specifically, the quantum pressure term we were discussing earlier suppresses growth at small scales. And this corresponds directly to an amplification of the pairwise velocities at large scales. So, it's two sides of the same coin, because the velocity, the main pairwise velocity spectrum is directly a function of the correlation function, which describes the probability of finding two objects at distance co-moving separation r from each other. And if it's far less likely to find galaxy clusters in this small scale, there's going to be an amplification of the likelihood of finding them in the large scale. I think that's the most sort of intuitive way to go about understanding these data. But the most significant objective of the project was to impose constraints on the abundances of axions. And we ran a very simple, Fisher sensitivity forecast. Essentially, we ran the analysis of generating data for the mean pairwise velocities over the mass window from 10 to the negative 27 to 10 to the negative 23 electron volts. And we, for like a specific prescription of galaxy survey, which we used CMB stage 4 and dark energy spectroscopic instrument DESI galaxy survey uncertainties. Essentially, what we wanted to see was, what's the minimum axion abundance these galaxy surveys can detect given a certain axion mass window. And what we found is that for axions of about 10 to the negative 27 electron volts, the minimum mass that would be detectable would be around 10 to the negative 2 to 10 to the negative 1 on that order. Specifically, it's like 9% with a 95% confidence level. And this increases to about 10 to the negative 23 mass, and you see that this minimum abundance sort of hits this threshold here. So essentially, with 95% confidence, our model can predict that, project rather, that axions may be detected between 9% and 20%. Although I should stress that this is very low resolution data, because we were only able to run it over 16 mass bins, which relative to the sort of inspiration study is not even half of what they used. I think that the essentially the takeaway from the project is that the study that this was based on did not use nonlinear power spectra to model these observables, and their mass window was a lot less constrained. It was between 5%, as I recall, to 100%. But we were able to constrain that to about 9% to 20%. So pending further statistical analyses of our data, I think that our data sort of reflects an increase in sensitivity, particularly in how constrained our data is relative to the original study. And I suspect that that likely comes from the greater physical motivation behind our model. But that's essentially the long and short of my project. I'm happy to discuss more if you have any more questions, but I see that we're out of time. But I thank you for all coming here today, and I appreciate your time. Thank you. If there's any questions, feel free to ask.
I think we can take one or two, and then.
And yeah, if you want to stay behind afterwards, I think we could. Yes, please.
When you say you were able to collect 16 bins, what exactly does that mean?
Yeah, so I wasn't too clear about that, but 16 mass bins. When you run a Fisher sensitivity forecast, basically you're varying you're like changing two variables to see how they relate in very loose terms. So you can think of, when I say 16 mass bins, I'm saying that we're performing this analysis with 16 sort of intervals between the low end and the high end. You can think of them as like Well, you can think of these mass bins as sort of an interval over which we're performing this analysis. If you take the limit as that those mass bins go to infinity, in principle, you should get a very smooth and graph that would minimize errors with our model. But that's computationally very expensive, and that's one of the suggestions that I propose to improve this model, is to increase the mass bins. But yeah, that's essentially what I mean. So is there any other questions? We can take one. I think we have time for one more. But, yeah, please.
Oh, and how much did you find yourself in the course of this project as an undergrad? How much material were you learning that was outside of your classes?
Yeah, well, my background is I'm only a physics specialist, and so I had never taken any astronomy courses before. So I had to, a month's worth of time on my part was dedicated to learning all about the astrophysical sort of foundations that you need to understand this project. And I tried my best to sort of convey that in as little of a time window as possible. But it took me about a month to sort of get to a level where I was able to understand material. Obviously, that's sort of that was only enough for me to get a working understanding of the project. But yeah, a lot of time is spent, exploring stuff out of the classroom. And if you're pursuing a research project in undergrad, you should expect to have to learn a lot more than what you see in your classes. But yeah, I mean, a lot of time is spent with that. So
Thank you.
Yeah, thank you very much for attending, and have a good evening.
All right. If anyone has any more questions, you could stay and ask. We've got the room furnished. Has no audio on this one. Just give him 10 seconds of splash screen.
I'm sure if it was still recording or not.
Yeah, I didn't really need it. Just there.